Hi friends, welcome back. So in the previous class we have seen even symmetry and odd symmetry. In the even symmetry always Bn is equal to 0. In odd symmetry always A0 and An both are 0. Bn is not equal to 0 here, An is not equal to 0 here. So in the even symmetry A0 may be 0, may not be 0. It's all depending on whether the wave is having area, positive area and negative area are same or not. If both areas are same, then we can say A0 value is equal to 0. Okay. Next, a very important symmetry which is half wave symmetry. What is this half wave symmetry? Let's check it. Third one, half wave symmetry. What do you mean by half wave symmetry? Mathematically, what is the condition it has to satisfy? Suppose if you take x of t signal, shift the signal right side or left side by half of the period. Shift the signal right side or left side by half of the period. If you get minus x of t, that is negative of the previous signal, then we can say this signal is satisfying half wave symmetry. I hope you understood. I am not giving any derivation here. I am just giving you the statement. So what if the wave is satisfying half wave symmetry? Then definitely the things will happen like this. A0 is equal to 0 always. An may not be 0. Bn may not be 0. So it's depending on, okay, only for odd values of n. Odd values of n. That means the signal, while you are expressing as a Fourier series expansion, it contains only odd harmonics. What do you mean by odd harmonics, sir? Like let's say omega naught, odd value, 3 omega naught, 5 omega naught, 7 omega naught, and so on. So these are nothing but the odd harmonics. Those kind of terms only present. So then we can say it is half wave symmetry. Remember, in half wave symmetry, A0 value is always 0, and whatever the remaining we are having, those remaining will have only odd harmonics. I hope you understood. Only odd harmonics, no even harmonics. That means we don't have any components like let's say sine 2 omega naught, sine 4 omega naught, like that. There is no terms, because that does not, that means they are having the even harmonics. So it is having only odd harmonics. That means that is x of t contains only odd harmonics. Only odd harmonics. Let me give you a waveform so that you can understand so how the half wave symmetry will look like. Okay. Okay. So let's observe. Is it satisfying even symmetry? Answer is no. Even symmetry not satisfied. Odd symmetry, that is also not satisfied. But it is satisfying half wave symmetry. It is satisfying half wave symmetry. How, sir? Suppose, let's see, if I shift the signal half of the period, if I shift the signal half of the period right side. So if I shift this half of the period right side means this part will comes like this. Will comes like this. Next, this part will goes like this. So whatever I have shown with a red ink, is it exactly negative of the previous one, blue ink, or not? So if I shift by half of the period, whatever the wave we are going to get is nothing but the negative of the previous signal. So this red wave is nothing but minus x of t, minus x of t. So from this we can conclude that it is satisfying half wave symmetry. If it is satisfying half wave symmetry, definitely it is having only odd harmonics. Now try to understand, does it have A0 value? No, definitely not. Why, sir? So whatever the positive area we are having the negative area also. So the positive area and negative area are equal, so that we can say A0 value is always 0. Is that clear? Okay. So this is what the half wave symmetry. So it contains only odd harmonics. I hope you understood. So it is not having even symmetry, it is not having odd symmetry, it is having only half wave symmetry. Some people may get doubt, sir, why can't it be odd symmetry? So let's see. If I fold it, this part will comes like this. So is it opposite to this one? No. So it is not satisfying odd symmetry, it is satisfying only half wave symmetry. Sir, in the examination, how can we see whether it is having half wave symmetry or not? For that I will give you one clue. So what is that? Consider one period, whatever which is convenient for you, So consider one total period, observe first half period and next half period. So let's see, for this only I am considering one total period. So this is what the total period, right? So if I consider one total period, how it look like? T by 2 t. This is the first half period, this is the second half period. If you observe carefully, whatever the wave at the first half period will be there in the second half period also, but with a negative sign. I hope you understood what I am trying to do. So whatever the wave we are having in the first half period is the same as that of the second half period wave, but only the change is negative sign. That means, so if I take this one here, so this will look like this. If I take the negative for this one, then it is going to be like this. So whenever to check the half wave symmetry, only one thing we have to do, consider one total period and observe first half period and the next half period. They must be exactly same with a different sign. That's only the thing we have to say. Okay. So take it and write down that point. How to check half wave symmetry? How to check half wave symmetry? How to check half wave symmetry? Consider one total period conveniently. Whichever is convenient to that period. It doesn't mean that only 0 to t or something like that. So you can take from here to here, whatever it is convenient for you, conveniently. And observe first half period and next half period, comma, if they are same with opposite sign, that implies we are having half wave symmetry. If they are not like that, then we don't have the half wave symmetry. Even plus half wave, even plus half wave symmetry. Then what kind of things we can observe? First, what about A0? Because it is having half wave symmetry, A0 value is equal to 0. Next, what about Bn? That is also 0. Why? Because it is a even symmetry. Next, An only present, not equal to 0. But see, I told you in half wave symmetry we are having only odd harmonics. So An is present, but that An value is present only for odd values of n and not for even values of n. So for odd values of n, for odd n. So now you tell me, we don't have DC term, we don't have sine terms. Bn is equal to 0 means we don't have sine terms. We are having only cos terms, and that cos terms are only present for odd values of n. Can I simply say it is having only odd cosine terms? Why? Because it is not equal to 0 only for odd values of n. So from this we can conclude that it is having only odd cosine terms. That's it. So contains only odd cosine terms. Odd cosine terms. Next, odd plus half wave symmetry. Odd plus half wave symmetry. Again, is A0 value 0? Yes. Why A0 value 0? From odd property also it is 0. From half wave symmetry property also it is 0. So that's why A0 is 0. An is also 0. Why? Because it is an odd signal, it is not having An terms. Next, Bn only present, Bn is not equal to 0. But this Bn is not equal to 0. Is it for all values of n? No, it is only for odd values of n. Why? I told you, because it is a half wave symmetry, it contains only odd harmonics. So that means for odd n, for odd n. Now you tell me, it does not have DC terms, it does not have cosine terms, and it is having only sine terms. That too, those sine terms having only odd values of n. Can I simply say odd sine terms? Yes. So contains only odd sine terms. Odd sine terms. Okay, take it. And we will see some questions based on this symmetry properties. From that you can understand. Okay. Check these two first. Is it an even signal or not? Yes. If you fold it, you are going to get the same signal because it is a symmetric. So it is even signal. Now, is it having half-wave symmetry? Yes. How, sir? Suppose if I consider a total period. So I told you, you can consider the total period with your convenient. That means if I consider this one total period, half period, half period. This half period we are having A, this half period we are having minus A. That means I told you. So if you consider total period, if you observe first half period and next half period, if they look exactly same with the negative sign, then we can say they are having half wave symmetry. Half wave symmetry. So if it is even plus half wave symmetry, what kind of terms it is having? So first you tell me. A0, 0. Next, an not equal to 0 for odd values of n, and bn is equal to 0. That means contains only odd cosine terms. Odd cosine terms. Next, coming to this one. So it is a odd symmetry. Why? If you fold it, you are getting a negative here. So it is a odd symmetry. And it is having half wave symmetry also. How, sir? Suppose if I consider a total period here with my convenient. First half period we are having A, next half period we are having minus A. I told you, if you consider total period, first half period and next half period are same with negative sign. It is having half wave symmetry. So A0, 0, an 0, bn not equal to 0 for odd values of n. For odd values of n. So this is the case. Then it contains only odd sine terms. Odd sine terms. Odd sine term. Is that clear? Okay. Let's see some more questions. Okay. Now you tell me, what kind of symmetry does it have? So many people will do mistake here. First of all, is it having even symmetry? No, there is no symmetric part. Is it having odd symmetry? Yes. If you fold it, this triangle will comes like this. So it is negative for this one. So I can say yes, it is having odd symmetry. Is it having half wave symmetry? Here the student do mistake. What is the mistake? Everybody thinks that it is having half wave symmetry, but not. It is having only odd symmetry, but not the half wave symmetry. Why, sir? See here. If you consider first half period and the next half period, they may look exactly same, but is not. Why? If you take this part and place it here, so this is what we are going to get. If you take the negative for it, this peak will comes here, but not here. So I mean, so if it is the negative for this, that is not going to be the same as this one. So I can say it is having only odd symmetry. Only odd symmetry. If it is having only odd symmetry, A0, 0, an 0, bn not equal to 0. For what values of n it is not equal to 0? It is not for odd values of n. It is for all values of n. Why? It is not having half wave symmetry. It is having only odd symmetry. So if it is having only half wave symmetry, then only we can say it is having only odd harmonics. But it is not having half wave symmetry. That means it contains all, that means even harmonics as well as odd harmonics. So for all values of n, that means contains all sine terms. contains all sine terms. There is no exclusion. Okay, so it contains all sine terms. Okay. Okay, I hope you understood what kind of symmetry the signal is having. Let me give you one more question, one more example. Okay, what kind of symmetry it is having? So it is a even symmetry plus half-wave symmetry. Why? If I consider a total period, for my convenience, I am taking from here to here. This is the total period I am considering. So if I consider first half period, next half period, both are same with a negative sign. So it is having half-wave symmetry also. So I can write A0 is equal to 0, AN is not equal to 0 for odd values of n, and Bn is equal to 0. That means contains only odd cosine terms. I hope you understood how to check the symmetries. Okay, take it. Okay, so you tell me, what kind of symmetry does it have? What kind of symmetry does it have? Okay, listen carefully. Is it having even symmetry? If you fold it, you are not getting the 2a here, so it is not having even symmetry. Is it having odd symmetry? That is also not there. We don't have the minus 2a here. Do we have the half-wave symmetry? That is also not there. Why? If you consider t by 2, if you consider next, so here we are having 2a, we don't have the minus 2a here. So that is also not the case. So it may look, it does not have any symmetry. It may look, it does not have any symmetry. So usually the first option is it contains all the terms. That means it is having the DC term, it is having the AC term, that is even harmonics, odd harmonics, and also cos, sine, everything. So, but my answer is, it is having only DC and odd sine terms. So it is having only DC and odd sine terms it is having. Why, sir? So here the symmetry what we are discussing is nothing but the hidden symmetry. So what we are doing is a hidden symmetry. So to understand the hidden symmetry, first understand this one. Suppose, let's say a signal x of t is equal to 5 plus, let's say, 4 sine omega naught t plus 3 sine 2 omega naught t. Okay. So if you observe carefully, what kind of terms does it have? It is having a DC term, first harmonic, second harmonic, okay, let's say, and so on, like that. Now, if I consider a signal y of t, which is x of t plus k, k is something like DC, a DC signal is added or some constant is added, then what will happen? What is the expression for y of t? 5 plus k plus 4 sine omega naught t plus 3 sine 2 omega naught t. I hope you understood. So let's see. By observing x of t and y of t, only the change what I have done is I have added a DC signal. So that means by adding a DC signal to any signal, what are the changes you are expecting? What is the change from x of t to y of t? Let's see. Before this, the DC value is 5. What is the DC value here? 5 plus k. First harmonic, no change. Second harmonic, no change. So the conclusion point is like this. By adding a DC value to any signal, that is going to change only the DC value, but not the harmonics. Can I conclude that like that? Yes. So by adding a DC value, the only change we are observing in the DC value, but not the harmonics. So this is a very, very important point. So I can write the conclusion point, or in general, suppose if I write a x of t expression like a Fourier series expansion, if you add k value, that is going to change only a0 value. I hope you understood. So let's say x of t in general I am writing, it is a particular example. If I take in general, a0 plus summation n is equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. If I take y of t is equal to x of t plus k, then where the change you are going to get? a0 plus k plus summation n is equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. So what is the conclusion I can make? By adding DC value, the only change we are going to get is a DC signal. Okay. By adding, conclusion, by adding a constant is going to change only the DC value, but not the harmonics. Okay. So DC value only is going to change, but not the harmonics. Coming to this question now. Now observe here. Let y of t signal. Take a y of t signal like this and observe it. Okay. Observe y of t signal. What do you get? By observing y of t signal, let's see. So forget about x of t signal. So tell me about the signal. What is the symmetry it is exhibiting? So it is odd symmetry plus half wave symmetry. Odd plus half wave symmetry. So a0 value 0, an value 0, bn is not equal to 0 for odd values of n. For odd values of n. Now, coming to x of t signal, what is the relation between x of t signal and y of t signal? What do you mean by that? What I have to do with this y of t signal so that I can get x of t signal? That means, what are the changes I can make to y of t so that I can get x of t? So if I push the signal upwards by a units, can I get x of t? So what do you mean by pushing the signal upwards by a units? That means we have to add a DC value. So if I add a DC value of plus a, then minus a will become 0, a will become 2a, and this is the signal what we are going to get. So in simple words, x of t is equal to y of t plus a. So just now we came to know, for any signal, if I add constant, what are the changes you are going to get? Only the DC value, but not the harmonics. So for this x of t signal, what is the a0? Previously its value is equal to 0 plus a. So it is going to change to a. Next, what is the an value? Harmonics does not change. So still an is equal to 0. bn is not equal to 0 for odd values of n. I hope you understood what I am trying to say. So even though it looks like it does not have any symmetry, but what is the symmetry we are discussing is called as hidden symmetry. The symmetry what we are dealing here is nothing but hidden symmetry. Hidden symmetry. It's a very important. In your examination, always they are going to ask the hidden symmetry. Why? It is difficult to find whether it is having the symmetry or not. Okay. First take down this one, then take that. So hidden symmetry. I will tell you how to find the hidden symmetry and those things. First complete this one. We can find hidden symmetry in a given signal. So in examination, check every time hidden symmetry is there or not. So let's see. Only the thing is how we can get the hidden symmetry is by manipulating the DC value. So forget about y of t. First find x of t. What is the average value? What is the average value here? For this signal, what is the average value? That is a0. How much? Over a period, what is the area? 2a into t by 2. 2a into t by 2 by total period t. T get cancelled, finally a is the average value. So by manipulating the DC value, that means bring it to 0. Bring it to 0. That means if I take x-axis like this, if I take x-axis like this, this is my x-axis, new x-axis. Now observe. So how much it is here? Same here. So now you can observe the symmetry here. I hope you understood. So but average value does not change. Average value is the same. So for this signal is A only. But by manipulating the average value, we can find the symmetry in the signal. I hope you understood. So I am writing that hidden symmetry can be observed by manipulating DC value, Next, A0 always calculated from the given waveform. What do you mean by that? So this is the given waveform. From this we calculated the A0 value. So that A0 value is same. So I hope you understood. A0 value is always calculated from the original waveform. Next, harmonics are calculated from the manipulated wave. So here, this is the manipulated wave. Y of t is the manipulated wave. So in that, we are finding out what are the harmonics it is having. So an is equal to 0, bn is not equal to 0 for odd values of n. So this information we could find from the manipulated wave. At A0, the value is calculated from the original waveform. That's what it is said. Okay, take it.